Hello student, in this video I am going to discuss about multiple regression. In general, there are two possible approaches to obtain improved fits in regression. The first is to examine a scatter plot and the residuals for linear nonlinear patterns, and then to make appropriate modifications to the regression equations. Now we'll obviously trying to understand how we can create that equation. The second approach is much more straightforward. Add more explanatory variables to the regression equations. We'll try to go through them. But when you add explanatory variables to the regression equations, we deliberately include only a single we deliberately can include single explanatory variables, or might be more than that. So when you include several explanatory variables in the regression equations, you move into the realm of multiple regressions. Some of the concepts from simple regression carry over necessarily to multiple regression, but some changes considerably. But what are the things that changes? Characteristics of multiple regressions is that graphically you are no longer fitting a line to a set of points. If there are exactly two explanatory variables, you are fitting a plane to the data. So try to understand that if you are going to input more than one explanatory variables, if there is exactly two explanatory variables, you are fitting a plane, not a line. In case of single linear regression, you are going to fit only a line. So in three dimension we are going to introduce a plan in case of two explanatory variables. There is one dimension of the dependent variable and one for each of the two explanatory variables. Though you can imagine a flat plan passing through a swarm of points, it is difficult to graph this on a two-dimensional screen. And if there are more than two explanatory variables, you can only imagine the regression plan. Drawing in four or more dimensions is impossible. The regression equation is still estimated by the least square methods. So regression equations still can be used as like the simple linear regression using least square method, that is by minimizing the sum of squared residuals. However, it is definitely not practical to implement this method by hand. A statistical software package such as Day3 tools is required. Simple regression is actually a special case of multiple regression, that is, an equation with a single explanatory variable can be considered a multiple regression equation. This explains why it is possible for use that tools multiple regression procedure for simple regressions. There is a slope term for each explanatory variable in the equation. The interpretation of these slope terms is somewhat different than in simple regressions, as explained in the following subsections. So, interpretation of regression coefficient in case of multiple regression. If y is the dependent variable, x1 and xk are explanatory variables, then a typical multiple regression equation has the form shown in the equation 10.9. So predicted y depends upon a plus b1 x1 b2 x2 like that, bk xk. If there are x1 to xk numbers of explanatory variables, where a is again the y-intercept and b1 b2 are the slopes of x1 x2 xk. Intercept a is expected value of y when all of the x's equals 0. Of course, this makes sense only if this practical for all of the x's is equal to 0, which is seldom is in this case. Each slope coefficient is expected change in y when this particular x increases by 1 unit, then other x in the equation remains constant. For example, b1 is expected change in y. B1 is expected change in y when x1 increases by 1 unit, and the other x's in the equation x2 to xk remain constant. So when you increase x1, then the b1 value has some input to the change of y. So but other values or other variables, explanatory variables, will remain constant when you increase x1. Simultaneously or similarly for x2, if you increase the value of x2 in the equation, then the value of other variables x1 or x3 or other till xk will remain constant, but the increase of x1 or x2 will have its impact on y, because the b1 is expected change in y. So when the other x is in the equation remain constant is crucial for the interpretation of regression coefficient. In particular, it means that estimates of b's depend on which other x are included in the regression equation. We illustrate these ideas in 10.2. So here again, suppose estimate and interpret the equation for overhead when both explanatory variables, machine hours and production runs are included in the regression equations. So to obtain regression output, select the regression from stateful regression and classification drop down list and fill out the resulting dialog box as shown in the figure 10.2. So using that tool, you can use this type of where this I is the data set, or this is the dependency, overhead is a dependency, and machine hour, production hour is the explanatory variables. Okay, so like that, fitted values as actual versus actual y values, or residual versus fitted values. So the main regression output appears in 10.21. 10.21, this is output appears. So the coefficients in the range of B18, B20 indicate that the estimated regression equation is B18 and B21. These are coefficients, constant, machine hours, production runs. So this is 3997 almost, 43.54, 43.54 coefficient, and 8862. Those are the constant, or you can say values of the coefficients. So here machine hour and prediction hours, production hour is different variables. So predicted overhead is the dependent variable. So if the number of production runs is held constant, the overhead cost is expected to increase by 43.54 for each extra machine hour. So if you production runs make constant, okay, production runs constant, held constant, then every unit of increase of machine hours will increase the predicted overhead by $43.54. And if the number of machine hours is held constant, if you keep constant machine hour, then increasing the production hours will increase the predicted overhead by 83.62. So here again you can make some inference that the cost of machine hours might be lesser than cost of production runs. So the Bendrix manager can interrupt the intercept 3997 as the fixed component of overhead. So whatever you keep it 0 or something else, the fixed overhead is 3997. So the slope terms involving machine hours and productions are the variable components of the overhead. It is interesting to compare equation 10.1010 with separate equations for overhead involving single variable each. From the previous section, these are like this. So you can separate these two equations. Is this equation 10.1010 in these two by using the previous section knowledge, where predicted overhead is 4861 plus 34.7 machine hours, or predicted overhead equal to 75606 plus 655.1 production runs. So note that coefficient machine hours has increased from 34.7 to 43.5, and coefficient of production runs increased from 6655.2 to 83.6. Also the intercept is now lower than the either intercept in the single variable equation. In general, it is difficult to gauge the changes that will occur when more explanatory variables are included in the equation, but it's likely that change will occur. So whenever so here you can see the values of the intercept and the values of the coefficient changes in this equation by, or decreases in this equation. So whenever you include more explanatory variables in a single regression equation, then this intercept value or the coefficient value will obviously change, but how it will change, it is tough to decide. So the reasoning is that when machine hour is the only variable in the equation, production run is not being held constant, it is being ignored. So in effect, the coefficient 34.7 machine hour indicates the effect of machine hours and the omitted production runs on overhead. But When both variables are included, coefficient 43.5 of machine hours indicates the effect of machine hours only, holding production runs constant. Because the coefficients of machine hours in two equations have different meanings, it is not surprising that they have different numerical estimates. Obviously, in this equation, the meaning of machine hours here production runs is omitted or ignored, but here it is included. So the meaning of this equation and meaning of these both two equations are different. So in case of multiple regressions, there are some insights with correlations and scatter plots. When there are multiple potential axes, means explanatory variables, for a regression y, it is useful to calculate correlations and scatter plots of y versus each x. So you can try to find out the correlation between x with the expected or explanatory variables access with every explanatory variable access with y. Try to find out the correlations. But remember that correlations and scatter plots are two variables only. They do not necessarily tell the whole story. Sometimes, as in this overhead example, a multiple regression can turn out quite differently than the might expected from the correlation scatter plots alone. Specifically, the r-square value for a multiple regression can be considerably smaller or larger than might be expected. Obviously, that can happen. So for this type of situations, we can go for a new technique to understand or interpret the standard error estimate and r square. The multiple regression output in figure 10.21, this one, very similar to simple regression output. In particular, cells C9 and E9 again show r square and standard error of estimate as C9 and E9. This is standard error and that is r square value. Also, the square root of r square appears in cell B9. The interpretation of these quantities is almost exactly same as in simple regression. The standard error estimate is essentially the standard deviation of residuals, but it is not given by equation 1011, which is different from the standard deviation equations, where n is the number of observations and k is the number of explanatory variables in the equations. So here you can see k is the number of explanatory variables in the equations, n is the number of observations, and ei is the E is the exponential value, I is for ith number of observation. Fortunately, you can interpret as C exactly as before. It is a measure of typical prediction error when the multiple regression is used to predict the dependent variable. In this example, about 2/3 of the predictions should be within the one standard error or $4109 of the actual overhead cost. By comparing this with the standard errors from the single variable equation from overhead 8585 by 9457, so you can see the R-square value, again the percentage of variation of the dependent variable explained by the combined set of explanatory variables. So for the Bandrix data, you can see that machine hours and production runs combines to explain 86.6% of the variation in the overhead. This is a big improvement over a single variable equations. Data are able to explain only 39.9% and 27.1% of variation in overhead. So if you go for multiple regressions, the changes can be more prominent and more explainable, and which is very important. And a square root of r square shown in the cell B9 of figure 10.21 of multipolar R is again the correlation between the fitted values and the observed values of dependent variables. For the Bandrix data, the connection between them is 0.931, quite high. A graphical indication of high correlation can be seen in one of the requested scatter plots, the plot of the fitted versus observed values of overhead. Like this is a scatter plot of fitted versus overhead, and it is most highly correlated. So what is adjusted R square? is a measure that adjusts R square for the number of explanatory variables in the equation. It is used primarily to monitor whether extra explanatory variables really belong in the equations. Means if we can go for more extra explanatory variables in the equation or not, that can be measured or that can be decided using the value of adjusted R square. Here you can see sometimes a regression equation is built by successively adding explanatory variables to an equation. As more variables are added, it is a mathematical fact that R square must increase, but it can be also decreases. However, it says that it cannot decrease. However, the standard error of estimates can decrease and the adjusted R square can decrease. Is signaling that the extra variables are not useful and should probably be omitted from the equations. So whenever the R square value decreases, then we can directly omit the extra explanatory variables, because those extra explanatory variables are not useful for the equations, which signals that by decreasing value of R square, which should not be, because R square must increase in a mathematical fact. And so that is why we should probably omit the extra explanatory variables from the equation. In fact, the purpose of adjust the R square is to monitor the whether equation is getting better or worse as more variables are added. That is what about adjusted R square. So it has a very important role in case of multiple regression analysis. So try to go through this concept again, try to use these equations and try to go from the first, from the simple linear regressions. The example is correlated with that also, so try to go through them. It is easy to understand. Try to calculate the values of standard deviations or standard error, estimated error and R square values, and try to find the adjusted R square value also. And if you increase the number of variables, how it can be changed, or how many numbers of extra explanatory variables can be added. Try to go through them. If you find any difficulty, please let me know. We'll try to overcome that through Google Meet. Thank you.